in vision and sensing program. For some of you, it's the first time. Oh, I should say, I'm Christy. I'm Deputy Director here at the Institute. For some of you, it's the first time here at the Institute, and a huge welcome. For others of you, it's lovely to have you back here again. For those of you who it's the first time, let me just say a few things. That you're able to go and use the Betty and Gordon Moore library over there if you want, which is a huge library which has every mathematical and related book under the sun. Also, you can go to the core building there and have a cup of coffee or something in the cafeteria there. And in nicer weather, it's quite nice to go up on the roof there. There's a quite nice grass area on the roof, and you can look out over here. It's a nice thing to do. Lots of information is displayed on here. I used to have to feel like an air hostess when I started doing these, saying emergency exits, fire exits, please, but in fact now all the information is up here for you, saying where lunch is. The only thing that sometimes confuses people is for program participants and workshop participants. So workshop participants, they have their lunch included in their package, so they just need to show their badges typically, and then they get their lunches. That's usually how it works. I'm assuming it's the same for this particular one. And program participants, because they get per diem, they pay for their own lunches. So there's sometimes people go, oh, that's a bit peculiar, but it's because they're getting per diems. So that is why there's the difference between the two. It's always exciting for us when we have new programs arriving and new proposals coming in. And one of the joys of my job is the complete, absolute spanning of the mathematical sciences that I see. We have the purest of the pure programs, and we have very different, widely ranging application domains. But for me, when this program proposal first came in, I was really excited. It touched my heart. It's just lovely for me because I don't work in this field, but a couple of decades or so ago when I was doing my DPhil, I used to spend a considerable amount of time hanging out with the computer vision guys in Oxford, both Andrew Blake's group and Andrew Zisserman's group. And so I kind of absorbed a lot of what was going on in the arena. So I'm 20 years or so out of date of what the research is, but I'm going to sit in on some of the talks and catch up with it. And so that's really, it feels to me like sort of friends have come home. And so that's going to be a really nice thing for me. It's also something that's really important to us is promoting and supporting diversity in computer science. And I just would like to see this. It's really lovely to see this block of in mathematics, to see this block of female mathematicians in the front, so that's really nice to see. You will see me wandering around with the camera from time to time, and that's important to get diversity on our material, so that's something you'll see me doing. Other than that, I just want to say I hope you have a fabulous week, and for those of you who are here for the whole programme, I hope it's a really exciting 4 months. Certainly I'm really looking forward to it, and so I'd like to hand over to Kei-Chen and on with the exciting programme that you've got for this week. Many thanks.
Good morning, everyone, and colleagues, friends. It's a great pleasure for me to welcome our program and workshop participants for this 4 months program. I'm here to represent my co-organizers, Carola, Chitun, and Michael and Andrew. And I remember 4 years ago, what's it called, April time, I was giving a talk in next door in Cambridge. I was sitting in the Carola office, and Chitun was visiting also. We started thinking about what about we could have an application for this program. We work on imaging and vision, and there's so many people we want to know, we want to sit together and do some work together, and so on. And then later on, we got Michael and Andrew, enthusiastically joined in. So we're really pleased that we got this far. And thanks for coming. This is not an easy time because teaching starts about to start in UK and Europe and in the US all started. So it's really a lot of commitment for you to come here. Okay, so. I just hope you will enjoy the program or this week if you just come for the workshop. And without further ado, I will introduce our first speaker for this moment. Our first speaker is Professor Joachim Weickert from University of Saarlandes. I know Joachim worked for many years and worked on many aspects of image processing and computer vision, and then one of my students visited him 2 years ago, and he learned a lot from his group. So today he's going to talk about efficient and stable schemes for 2D forward and backward diffusion.
Yeah, thank you very much for the kind invitation. It's really a great pleasure being here and having the opportunity to talk about a topic which is dear to my heart and which is actually referring to research I'm doing for about 15 years now. And I would like to mention this topic is joint work with Martin Welk from Hall in Austria. We have a problem here. Seems to be connected, yeah. It's optimistic. Okay. Okay, so this is the first time it works with HDMI. Yeah, it is research where I've been working on for about 15 years, and it's joint work with Martin Welk from Hall in Austria and Guy Gilboa. He doesn't know about his luck right now, but it refers to some older research with him. And yeah, what is it all about? It's about the things you're not supposed to do. We love these things since our early childhood, and also there's a long history for that if you think of Adam and Eve. So these were the first people who are doing things they are not supposed to do. And well, if Adam and Eve were to work on parabolic PDEs, what would they do? Well, my claim is they would look into backward diffusion processes, because that's exactly where everybody warns you of. Backward diffusion is a classical example of an ill-posed process where small perturbations may lead to huge perturbations in the solution, if the solution exists at all. And a classical example of an diffusion process which involves backward diffusion is the so-called FAB, or forward and backward diffusion process. And for that diffusion process, the diffusivity can become negative in a certain gradient range. And you will see that the gradient, it can be regarded as a gradient descent of an energy which looks really unpleasant. I will give you some examples later on. And the goal of my talk is basically to try to establish some sort of a theory for this forward and backward diffusion. Since this is very difficult in a continuous setting, and I think it's unlikely that somebody will come up with it within the next few years, I would like to focus on space discrete and fully discrete models. And also I would like to come up with adequate algorithms which do what they are supposed to do, and secondly, which are efficient. And I would like to emphasize that this is really research for the fun of it. It's not driven by any concrete application. There's no specific funding behind it. There are no deadlines, so it's just research for the fun of it. Okay, so here's the outline of my talk. I would like to give you some review on what is known about this forward and backward diffusion so far, and then I would like to focus on our results on space discrete diffusion and fully discrete diffusion. Furthermore, I would like to tell you a little bit more about schemes which work efficiently from a numerical perspective, and I will give you some experiments and conclude with a summary and some outlook. Okay, so in order to understand FAP diffusion, it is useful to remember the first diffusion, the first nonlinear diffusion model in image analysis, which goes back to Perona and Malik. So imagine we work on a, say, rectangular image domain omega, and we are given some bounded image f. Then the idea behind the Perona-Malik filter is you want to create a family of filtered versions of this image by regarding it as an initial state of a diffusion process, which is governed by a nonlinear diffusion equation. du by dt is the divergence of a diffusivity times the gradient of u, and you assume homogeneous Neumann boundary conditions, so that means you just have reflecting scenarios at the boundary. And typically what Perona and Malik assume is that you have a diffusivity which is monotonically decreasing and which remains a positive function for all gradients. So the philosophy is that whenever you have an edge, your gradient magnitude is large and you would like to reduce your diffusivity to preserve the edge, and in the interior of a region where the gradients are pretty small in magnitude, you would like to have a larger diffusion. You can easily derive this diffusion process as a gradient descent of an energy which may be non-convex but typically monotonically increasing energy, and the potential or the penalizer psi is related to the diffusivity via psi prime equals the diffusivity. So that's what you easily get from the calculus of variations. Okay, forward and backward diffusion goes one step further. It goes back to Gilboa, Sochen, and Sevi in 2002, and they aimed at a stronger sharpening effect than the Perona-Malik filter, and to that end they allowed the diffusivity to take also certain negative values. And actually the model I'm interested in, do we have some chart here? Yeah. Is essentially of that type here. We have a diffusivity which is positive and may become negative, and then, well, it depends what you want to have. So it's bounded here by some minus C2, and what we essentially need is that my C1 is larger than my C2, which is larger than 0. And of course you would like to have something which is smooth here as well. No? So that's essentially the type of models I'm interested in. And these are all the requirements that we need here. And the interesting thing about that is actually the potential function which you have can be non-convex and even non-monotone. So it can have really very unpleasant shapes. So here are a few examples. I will come to these diffusivities in more detail towards the end of the talk. So that was an early model of an FAB diffusivity. It corresponds to potential which looks like that. Class of diffusivities which goes back to Smolka is taking negative values and remains in the negative domain. So the corresponding energies look like this. And I would even like to go one step further. I would like to have a diffusivity which remains negative and does not even tend to 0 for large gradients. So actually here you're bounded from above by a concave function. Huh? And we want to minimize this. So that's the challenge actually. Huh? And if you want to see it from a geometric perspective, you can basically decompose the diffusion process in diffusion along the gradient and perpendicular to the gradient. And then you will see that after some manipulations, you will see that in that local coordinate system, you may have a factor in front of the flow line diffusion here, which may take any sign, and your diffusivity can also be positive or negative. So that means also the diffusion along the isophotes, along the isolines, can take any sign. So in the worst case, you have backward diffusion in both directions. No? And that's, of course, a challenge to come up with stable numerical schemes and to establish some sort of a theory for that. And so what is available so far? Well, first of all, one should mention that the classical results for nonlinear diffusion filtering, the classical theory, which can be found, for instance, in my monograph, cannot be applied to that setting because it requires some sort of positivity of the diffusivity or a positive definiteness of the diffusion tensor. In general, in the continuous setting, there's no well-postness theory available, and as I said, I'm rather skeptical that there will be one in the next few years. Gilboa and colleagues, they observed that classical, straightforward, standard implementations do violate maximum-minimum principles. So it is basically an unstable process. And in order to stabilize it, one can, for instance, add some sort of a biharmonic regularization or add a fidelity term which prevents the solution to go too far away from the initial image. But of course, it means you are considering a different model there. And what Martin, Guy, and I did at the SSVM conference 2009 was to look into semi-discrete and fully discrete models, and we came up with some sort of a preliminary scale space theory in a space discrete setting where we had established well-postness and extremum principles. I will review these things here as well. In the fully discrete setting, things were not that satisfying. We only could look into 1D schemes, and we found out that you need really extremely small time step sizes in order to guarantee stability and reduction of the total variation. There are no experiments, no 2D theory, and of course the goal would be to go somewhat beyond. So can we get a more complete scale, space discrete and fully discrete theory, and in particular, does it lead to practical algorithms for images? So let's have a look at the space discrete setting. What does this mean? So here the goal would be to establish basically a well-postness theory, and as I mentioned, the classical theory is not applicable here. However, with this new theory that I'm going to describe, which is a modification of the classical theory, I would like to show you that FAB diffusion can be interpreted within that framework, provided that you are doing some non-standard things with your space discretization. Okay, let's start. So that's the general nonlinear diffusion equation where I've just split the divergence expression into an x and a y part here. And of course, if you want to apply some standard finite differences, your evolution in if you apply them in space, your evolution looks like that. Your partial differential equation becomes an ordinary differential equation in every pixel. So that means you get a system of ODEs. And you get basically parts which describe the interaction of your central pixel ij with its 4 neighbors here. Its right neighbor, its left neighbor, its top neighbor, and its bottom neighbor. And the diffusivities are averaged basically in these 2 pixel interactions. Okay, let's write this a little bit in a little bit more compact way in order to understand the basic structure. So first of all, we can get rid of the double indices if we just replace them by a single index. And then it looks like this. Each term basically is just the difference between the neighbor and the central pixel. And you have some averaging of your diffusivity in the central pixel and in the neighbor. And you divide here by h1 squared or h2 squared. So this is how it looks like here in a more general setting. And of course, if you want to get away from individual pixels, you can stack them into a vector, and then actually you have a compact notation as an ODE system, which looks like that. Du by dt, use your vector with the pixels here, is some matrix which may depend in a nonlinear way on your evolving image times the image vector itself. And the matrix is a pretty sparse matrix, so it has only positive entries for the neighbors here. So these are your positive factors, and for each positive neighbor you get a negative entry in the central pixel, and apart from that your entries are 0. So it's a fairly sparse matrix which describes the diffusive interactions. Now I would like to come up with a general theory for processes like that. It does not necessarily mean that it is directly applicable to this specific scenario. We'll discuss that later on, but here's the more general framework. So we are looking at an ODE system of this structure here, so a dynamical system, and I would like to assume that this matrix A, which is a function of the evolving image, has 6 useful properties. First of all, Lipschitz continuity, which helps to establish existence and uniqueness by the Picard-Lindelöf theorem. Then for diffusion, it's typical to have symmetric matrices, and the row sums and the column sums are vanishing, so I can assume that the row sums are vanishing, the column sums follow by symmetry then. And then I need some sort of non-negativity requirements. First of all, I assume that at extrema my matrix entries are non-negative here, which describe the correspondences here with the neighbors and with the other pixels apart from the central pixel. And in the neighbors itself, I require actually strict positivity here. And last but not least, I also require some sort of connectivity. So the mathematical notion for that is some irreducibility of the neighborhood relation. So I assume that my neighborhood graph is connected. So these are the 6 requirements which I have. And what can be shown? Well, we have established the following results. So first of all, the process is well posed in a global setting. So we have a unique smooth solution. It's C1. It is well posed also in that sense that it depends continuously on the initial image and on the right-hand side of the ODE system, which contains typically also the diffusivities. No? Then, result from the divergence formulation and the reflecting boundary conditions is that you have average gray level invariance, so that means your average gray value does not change over time. Let's abbreviate it by mu. You also get a maximum minimum principle telling you that your solution remains within the bounds of the original data for all times. And in order to establish convergence, it is useful to look into Lyapunov functionals, and we came up with a specific class of Lyapunov functionals which is applicable here, namely the range. So you take your largest gray value and subtract the smallest gray value, and it can be shown that this is an entity that decreases over time and is bounded from below, actually by 0. And with that results on Lyapunov functionals, one can show that the process converges to a constant steady state. Here are a few remarks on the proof. First of all, well-postedness, you get it locally almost for free by the Picard-Lindelöf theorem. So basically Lipschitz continuity is responsible for that. If we guarantee that the column sums are vanishing, we get average gray value invariance. And the max-min principle is established in 2 ways. First of all, you establish it locally by non-enhancement of local extrema, and then you extend it by continuity arguments. The maximum minimum principle together with the local well-postedness give you global well-postedness, and the rest requires these non-negativity and irreducibility assumptions. As important intermediate steps, you can show that your range is continuous, that it's bounded, and it's piecewise differentiable. The right-hand side derivative, let's denote it by y prime plus. Then it is smaller or equal than 0 for all times, and the events when it is 0 are discrete. So it cannot happen that it's 0 for a longer time unless U is flat. And with these results, we can get the convergence results. So actually, this theory is quite general. So in particular, it does not rely on any Cartesian grid. So if you're interested in graphs, for instance, you can directly apply it also on graphs. You just have to make sure that these somewhat abstract requirements are met, and then it also holds on graphs or surface data or whatever. So it's not linked to a certain grid structure so far. Okay, now of course we want to go back. We want to go back to the FRB diffusion. If we apply it to an image, what does this mean? Can we apply this theory? Well, a few things are unproblematic. So first of all, these requirements S1 to S3, they are satisfied for any diffusivity, and by the boundary conditions, the reflecting boundary conditions, that's no problem at all. Also, of course, if you have a Cartesian grid, you have a neighborhood relation which connects all the pixels, so that's obvious. So that's the easy part. The problematic part is guaranteeing that these properties S4 and S5 are met, namely that your off-diagonals at extrema are positive and or non-negative, and in the neighborhood of extrema you even have positive off-diagonals. Why is this the case? At first glance you would think at extrema your gradient is vanishing, so I have a positive diffusivity, no problem at all. Well, that's the continuous theory. Let's have a look at what you would typically do with a discretization. So if you have a diffusivity like that, and you discretize here your gradient magnitude, for instance, by central differences, well, nobody guarantees you that this will be 0. In general, you can expect that this will be something which is positive, even at extrema, at discrete extrema. And that means if my argument is somewhat is positive here, it could even happen that I have a negative diffusivity here. No? So that means it's not trivial at all to ensure non-negativity of the off-diagonals at extrema. So how can this be avoided? Actually, the solution is just using a clever trick. You have to get rid of discretizations like that. You have to use better discretizations, and here is one possibility. You could try to approximate the gradient magnitude here by the product of the forward difference times the backward difference in x direction, and if this turns out to be negative, then you are actually at an extremum in x direction, and so you replace it by 0 here, so you have the maximum operation, and you can do the same in y direction, and actually by definition this really ensures that at discrete extrema you get here an argument which is 0. No? So it looks a little bit strange at first glance, but you can easily convince yourself that this has the same quadratic consistency order as the standard discretization here. That's the standard discretization. That's what you would call a non-standard discretization, which combines forward and backward derivatives here in a multiplicative way. And with that, actually, you get what you want. We have to show that the off-diagonals are non-negative at extrema. Well, first of all, this approximation is 0 in extrema, and that means here we get the diffusivity in 0, which is C1, which is really positive. Secondly, we have to make sure that in the direct neighborhood of the extrema we get positive off-diagonals. Well, these are the entries in of the direct neighbors here. So it's the diffusivity in the extremum and the diffusivity in the neighborhood. Well, and of course if I add them, since I have assumed that C1 is larger than C2, I can be sure that what I get is actually positive. So this is really essential here in order to get a nice theory. And of course, if the other pixel is not a neighbor, we have a 0 interaction, and that means that's also uncritical here. No? So that means with that discretization, we are in a position where we can come up with a space discretization which is actually in accordance with the theory that we have. And this is summarized here in the theorem, so it just tells you if your diffusivity is fulfilling these requirements here, and if we are using the non-standard discretization, all the 6 requirements of theorem 1 are met, and this implies that we have a complete theory, even if it is an FAB diffusion process. So that means it's well-posed, the average gray value is constant over time, an extremum principle holds, we have a class of Lyapunov functionals, Lyapunov functions given by the range of the image, and we are guaranteed that everything converges to a flat steady state. Also, this result is not restricted to 2D images. Actually, it can be easily extended to any dimension, so that's not a problem at all. Okay, so that was the space discrete, but the space discrete framework, which is still continuous in time. What happens if we discretize in time? Well, of course, we get the fully discrete framework, but there might be problems involved here as well. So let's have a look. So let's assume we have actually a dynamical system which satisfies all our space discrete requirements. And now let's use the simplest discretization in time you can think of, namely an explicit Euler forward scheme. It just means you have a forward difference in time direction here, and you evaluate your right-hand side at the old time level. No? It's called explicit scheme because you can explicitly compute here your new time level without solving linear or nonlinear systems of equations. So we have a time step size tau, and uk is just supposed to approximate u at time k times tau. No? Well, if we assume that we have something like that with a smooth diffusivity, I can introduce 2 technical terms. I can denote the range here of the initial image by r, and of course, since the function is smooth here and C1 is larger than C2, I'm guaranteed that there is here some interval here where this relation also holds for larger gradient magnitudes, and this length of the interval can be written as some value omega times r. No? So that means here omega is defined in such a way, and r is just the range of the initial image. No? Okay, and with that, the following theorem has been proven by us. Namely, if we take the explicit scheme in the 2D case and make sure that the time step size satisfies here a fairly restrictive condition here, you don't need the details. You just should remember that this can be pretty small, this bound here. Then actually you get all the properties you want to have, namely the same properties that you also have in a space discrete setting, namely the process is well posed. Well, that's trivial, it's just a matrix vector multiplication. And as such, of course, it also depends in a continuous way on perturbations of your initial data. Your average gray value is preserved over time. You do have a maximum minimum principle, and you get some sort of Lyapunov sequences, the discrete counterparts of the Lyapunov functions. They are described by the range at the individual time levels. So this is also something which is decreasing in the time levels and bounded from below. And with that, you can also establish that everything converges to constant steady state. Okay, so basically it means we also have a complete discrete theory, which at least applies for an explicit scheme, provided that you choose sufficiently small time step sizes. A few remarks on the proof. Basically, the maximum principle, which is one of the most important parts of the proof, requires 2 steps. First of all, one shows that pixel in a maximum does not increase. So basically that's a result from this here. And the neighbors of your maximum pixel are supposed not to grow in excess of this maximum. That is actually the more tricky part, which typically gives you the more severe time step size restriction. So that is responsible for bounds like that, actually. And you probably might think that, well, you could use implicit schemes in order to get absolute stability. Well, this is true for forward diffusion, but for backward diffusion, this is no longer true. And for forward and backward diffusion, it's also not true. And the reason is relatively simple. For forward diffusion process, the smoother results are in the future. So if you want to have a stable scheme, you should look into the future, or in other words, you should use an implicit scheme. For backward diffusion, the smoother results are in the past, so a more stable scheme should look towards the past. So actually an explicit scheme is more stable than an implicit scheme for backward diffusion. So that's a bit counterintuitive at first glance, but you can find reasons for that. On top of that, in the 1D case, we have shown that monotonicity is preserved. So that means if we have a monotonically increasing function in 1D, it remains monotonically increasing also under FIB diffusion. And the total variation is reduced over time. Okay, so that means basically we even have a numerical scheme. No? We don't have only a theory, we also have an example where it works, namely an explicit scheme provided that the time step size restriction is satisfied here, and it looks like that. Well, actually in practice, this is a very severe restriction. It typically requires time step size in the order of 10 to the power of -5, 10 to the power of -6, whereas for forward diffusion you would use in 2D something like 0.25 or something like that, no? If your grid size is 1. So that means it is really prohibitive. It's an impractically small time step size which you need in order to guarantee stability, on top of the fact that you need this non-standard discretization. But at least in theory it works. So the question is, can we do better? Can we get more efficient schemes that basically inherit the nice properties that we have from the theoretical framework? And the answer is yes. However, you have to work for it. You don't get it for free. And first of all, we should analyze what's the reason for this severe time step size restriction. Actually, it comes from a lot of very pessimistic a priori estimates that you do right from the beginning based on your initial image. You could do much better if you're using a posteriori estimates which you generate on the fly during the image evolution. So that's one step. And secondly, these estimates, they do not hold everywhere. They only hold at a few locations in space and at a few instances in time. So that means a few pixels basically create very restrictive time step size restrictions here, very prohibitive time step size restrictions, whereas we would like to use much larger time steps in all the other locations in space and in time. So actually that also suggests a remedy. No? So we would like to act as locally or as adaptive as possible, not only in space but also in time. And the best way that we have found so far consists of looking at so-called 2-pixel interactions. And it just means you want to have an interaction in horizontal or in vertical direction. And actually this is not as unnatural as it may look like. Namely, if you just go back to your explicit scheme, your explicit scheme in 2D actually contains 4 2-pixel interactions. That's the interaction between the central pixel and its right neighbor, central pixel and left neighbor, central pixel and top neighbor, and central pixel and bottom neighbor. No? So you basically perform 2-pixel interactions, but you perform them simultaneously in explicit scheme at the same time level. What I would like to do now is, actually I would like to perform them sequentially. So in an asynchronous way. And the reason for that is very simple. A 2-pixel interaction is something which I can analyze in a straightforward way with respect to its stability. And if you have a sequence of stable processes, the result which you get at the end is stable. If every process satisfies a max-min principle, of course you get a max-min principle at the end. So that's the first trick. And as stability criteria, I use that if you have 2 pixels and these are the gray values, that these gray values should not flip if I have forward diffusion. So the worst case that should happen is that they become balanced. And the second story is for negative diffusivities. Of course, I must have non-extremal pixels. And then I would like to make sure that these non-extremal pixels do not grow in excess of the maxima or minima in the neighborhood. So that's the second stability criterion. And actually, each of these stability criteria gives me a time step size restriction. So that means for each of the 2 pixel interactions which I have, I can obtain a local time step size bounds. No? And that's the most localized interaction you can think of, as long as you want a conservative process. And of course, if you do this in a certain order, the big problem is that your result might depend on the order in which you pass to all your pixels. So in order to be fair and unbiased, what we do is we randomize the order of the 2 pixel interaction. So we don't do it in a specific order. We choose it randomly. And in order to make sure that certain structures where the time step size restriction is small and other structures where the restriction is large, that they are somehow synchronized, we introduce so-called sync times, where all the pixels are supposed to reach the same time after some part of the evolution. So typically, as a sync time, you can think of a time step size of a forward diffusion process. And that just means that each pixel pair has its time account, the time that remains until the sync time is reached. And if this time is still large, the probability that I choose this pixel pair is larger than if the time is small. So the probability is chosen as an entity which is proportional to the remaining time up to the synchronization. So what we have shown is that this approximation here of the explicit scheme is conditionally consistent. So it has an approximation error which looks like that. And that is basically, that is the greeting which you get from the splitting that you introduce here. No? So you have to pay for it, of course, in some way. And actually that just means if tau divided by h to the power of 4, if this remains bounded, then the process is consistent. So that means if tau and the grid size h tend to 0, you approximate your PDE. No? Oops. Let's try it again. Just remove it. Don't touch. Okay, conditionally consistent. That's what we get. So that's the main price we have to pay, basically. But we are extremely consequent. We are as consequent as we can ever be when it comes to adaptivity or locality of the scheme. And let's do some experiments to see how all these ideas actually perform in practice. So here's an example of a diffusivity which I choose in my experiments. Actually, it looks like that. It has 2 parameters, a contrast parameter which basically tells you where it becomes negative, and a stretching parameter, kappa, which tells you basically something about the slope here. The runtimes which I report are resulting from a standard standard processor, single core implementation in C. And so the first experiment just compares standard discretization and non-standard discretization. No? So if you just take the forward and backward diffusion and discretize in a naive way, even with extremely small time step sizes, 10 to the power of -5, and this is now 1 million iterations, you get results like that. So it is unstable. You cannot use it for approximating diffusion processes like that. On the other hand, with the non-standard discretization, which makes sure that in extrema we are really having a gradient approximation which is given by 0, and that means we have a positive diffusivity, we are stable. Same time step size, also 1 million iterations, you get a filtered result which is basically what you want to have. So that's the first result. So we see that the non-standard discretization is essential. You cannot cope without that if you don't do any other tricks here. The second experiment now compares the explicit scheme with a small time step size restriction versus the 2-pixel scheme, which is as adaptive as possible with its stability restrictions. So here are the two results, and I think I can zoom into them. So that's the first result for the explicit scheme, and that's the result for the 2-pixel scheme. Once again, explicit 2-pixel, explicit 2-pixel. They're not identical, but of course they are qualitatively absolutely comparable. So here I have a time step size of 10 to the power of -5, which is realistic under these time step size restrictions, and I need basically 1 million iterations to reach a reasonable stopping time of 10. That takes me 66 minutes. Here I just need 100 synchronization steps of a time step size of a sync time step size of 0.1. And actually, for most of the pixel pairs, I'm pretty close to it. So you see actually the average time step size is 0.991. So I'm very close to the 0.1, so that means I have only a few pixel pairs which slow down the process. And at the end of the day, it just means for this 100 sync time steps, I need a computing time of 7.73 seconds, which results in a speed up of a factor 544, which you get basically not for free, but you can do essentially the same things as with an explicit scheme. You just localize it as much as possible in space and time. And that means, of course, now we are in a position where we can also do long time calculations, for instance, compute scale spaces with this forward and backward diffusion. So here you see a really noisy image, and you see the scale space behavior, so that means the evolution over time. And what you can observe is that the scheme does exactly what it's supposed to do. For t tending to infinity, it converges to a flat image. It is actually useful for denoising, which is not clear at all if you have a forward and backward diffusion process. And in between, it gives you a signal enhancement. You get a contrast enhancement here by the backward diffusivities. Here the contrast decreases, and after some time it just breaks down and converges towards the average grayscale. No? So that means you can really do computations with sufficient efficiency, and you can get all the properties that you have from theory. They are preserved also in a practical setting. And I mentioned different types of diffusivity, so let's have a look into these different types. So the one which I just showed you all the time was actually what I call here type 2 diffusivity, which looks like that. Diffusivity tends to 0 as the gradient tends to infinity. So it corresponds to potential of that shape, where we have a horizontal asymptote. But of course, it's a non-convex potential. So the early diffusivities of FAB type, they looked like that. They correspond to a potential which is still bounded from below by a convex function. So this is the easier class of problems. And as I said, I would also like to look into scenarios like that, where the diffusivity remains negative, and that comes down to a potential function which is actually bounded from above by a concave parabola. And the goal is, as I said, to minimize actually energies like that. And here are some technical details how this diffusivities look like. I think I don't want to bother you with too many details here. Here are the results. So for the type 1 diffusivity, you get an enhancement, but you see it is relatively smooth at edges still. For the type 2 diffusivity, it is probably an enhancement which you would expect in a practical setting, and if you just want to go further with a type 3 diffusivity, actually you get pretty checked edges, but this is a process which is using a negative diffusion or backward diffusion in both directions along the isolines and along the flow line. So that means that's the worst we can think of. Nevertheless, it is possible to have a stable discretization which gives you the results which you can expect here. Okay, so time to summarize. So what I wanted to show you is that actually it's possible to establish a rigorous theory for forward and backward diffusion if you restrict yourself to a space discrete or fully discrete setting. And the requirements on the diffusivity are pretty mild, so basically you need a smooth diffusivity of that type where the lower bound basically does not exceed the upper bound here in its modulus. That's all that we need, and for an explicit time discretization it's essential that we have a non-standard space discretization. It's also essential for the space discrete theory already, continuous in time. So it's not a specific feature of an explicit scheme. As an alternative to this explicit scheme, which suffers from very restrictive time step size bounds, I came up with a localized 2-pixel interaction which combines 4 features which are not very common in image analysis. First of all, the 2-pixel interactions are not that common. We have done a little bit in our group mainly, but they are not so widely used. We have local time step size adaptation, so sometimes there are some adaptations in space, but in time this is usually not done in image analysis. And we have introduced asynchronous splitting, sequential splittings, in order to come up with a stability theory which is easy to establish. So that's because we are lazy, basically. And in order to get rid of any bias due to this asynchronous ordering, we introduced some randomization. And as a result of these efforts, you could see that it's possible to achieve speed-ups by 3 orders of magnitude, turning backward diffusion into something which you can compute in reasonable time. So that means it is something you might want to consider for image enhancement applications in practice as well. And, well, the bottom line is, well, if this looks evil to you, these backward processes, you should not fear them. You should try to understand what's the reason for their instability and try to overcome this instability by appropriate numerical decisions and by an appropriate theoretical framework. Okay, so what is our current and our future work? Well, currently we are looking into options to get rid of the asynchronous splitting, because this is something which introduced some conditional consistency which has some bounds which are more severe than we would like it to be. So perhaps we can achieve more general conditional consistency bounds with some alternative schemes. That's our hope. And of course it would be very challenging to try to analyze all these things a bit more from a variational perspective. If we have potential functions like that and we would like to find minimizers, it is definitely unclear how many minimizers you have and why does the FIB diffusion pick up a very specific minimizer here. It seems to do some useful thing which is not that easy to understand from a purely variational setting, so that's one of the challenges for the future. And of course this might also be a blueprint for backward parabolic processes beyond FIB diffusion and also related processes. There are shock filters in the literature, for instance, which are kind of parabolic, backward parabolic and hyperbolic processes and so on. So perhaps we can learn something from what we have done here and apply it also to other processes. Here are a few references if you would like to read a little bit more about that. So some first work has been published at the Scale Space and Variational Methods Conference in 2009. It was basically a slow 1D numerics, and the full story, the 2D 2-pixel schemes, this has been published very recently at this year's SSVM. You can download both papers from our publication webpage, and if you are a postdoc and you're interested in joining our group, we have an opening at the moment in an ERC advanced grant, which I received for research on in-painting-based image compression. Basically, you should have some expertise in optimization, PDEs, or variational methods, and just send me your CV. Thank you very much.
Joachim, you are proving that the diffusion will give you a constant value, and you are using the Lyapunov method. Now, the Lyapunov says that this Lyapunov function is decreasing and is lower bounded, but it doesn't say that it's decreasing to 0.
You need a strict. You need some additional arguments. You need some additional arguments in the proof. Yeah. It's actually a bit more complicated than I showed you here.
I would like to ask you: did you consider this old method that Denis Gabor proposed a long time ago, in which he says essentially combine processing along the ISO lines and in the direction of the gradient, because these are very exactly.
Basically, you can phrase it. You can phrase it in that class.
So the question is, this can be considered like a theory that explains this.
Yes.
A discrete version of the Gabor scheme.
Yes. Yeah. So basically all you have to do is you have to find a function which approximates the switching that Gabor does basically, or the combination.
Yeah.
And then it is covered by the theory as well. Yes.
Yeah, but Gabor doesn't say that it should be a function of the gradient.
Yes, both. No?
Like
it just combines both of them.
It just has some weighting between the two. Yeah.
I'm not sure what that means here. It just means we should, if this is a constant, I don't think it's covered then. No.
Okay,
Probably not.
very interesting. Thank you very much.
Probably not. But I'd be happy to discuss this further. So perhaps it could be extended.
I suggest we have a coffee now and then keep asking questions. I hope you're not leaving yet. Thanks a lot.
Okay, thank you.